Hi, we're going to look at the math of lenses. This might be one of the shortest videos I'll ever make because you essentially already know the math of lenses because it's identical to the math of mirrors. So all we have to do is look at the couple little differences and maybe do a practice problem and we'll be done. A real quick recap of lenses. A lens that looks like this is known as a converging lens or also a convex lens. A lens that looks like this is called a diverging lens, also known as concave. Now here's the big difference between the two. Converging lenses are called convex. Converging mirrors are called concave. Diverging lenses are called concave, and diverging mirrors are called convex. What the mirrors and the lenses do comes from the converging and diverging part. The convex and concave come from the shape. If my eye is over here and I look at an object that goes like this, that is a concave shape. That's why this lens is the concave lens. But the mirror that looked like that was called the concave mirror. If I'm looking at something that looks like that, that is convex. That's why I actually don't like the idea of calling them convex and concave mirrors and lenses. I like converging and diverging because it tells what it does. And converging mirrors and converging lenses do the same thing. They take parallel light and converge them to a single focal point. In the case of lenses, the light passes through. In the case of mirrors, it bounces off and does that. A diverging lens takes parallel light and spreads it out, diverges it back from a single point. Math-wise, it's more consistent if we talk about converging and diverging. Converging lenses have positive focal points, and diverging lenses have negative focal points. The types of images you create. A converging lens can make 3 types of images, just like a converging mirror. A diverging lens can only make 1 type of image, just like a diverging mirror. So they're really, really very, very similar. The math is actually identical. Let's do an example. What is A, the position, and B, the size of the image of a 7.6 centimeter high flower placed 1 meter from a plus 5.0 millimeter focal length camera lens? First thing, write down some information. Okay, we know the height of the object is 7.6 centimeters. We also know that the object distance is 1 meter and that the focal length is plus 50 millimeters. The first thing I have to do is get all of these numbers into the same units. It's going to be nothing but trouble if I don't. I'm actually going to go with centimeters here, and I'm going to take the object distance, and I know that 1 meter is 100 centimeters. Also, I know 50 millimeters is 5 centimeters. Now that they're all in centimeters, I can use the equations. So the first thing we're going to do is find the position. When we say the position, what we're really looking for here is the image distance. 1 over f equals 1 over do plus 1 over di. That means 1 over di equals 1 over f minus 1 over do. That would be 1 over 5 centimeters minus 1 over 100 centimeters. That is going to give me that 1 over di equals 0.19, and so di equals 5.26 centimeters. Part B, finding the height. I could calculate the magnification first, but I know that the magnification is equal to hi over ho, which is also equal to negative di over do. I don't have to calculate the magnification first. I can, if I want to, just use this, the ratio of the heights is equal to minus the ratio of the distances, and that's what I'm going to do. If I solve this for the height of the image, I'm going to get that it's equal to negative di over do times ho. Now I can just put the numbers in, and that would be negative 5.26 centimeters over 100 centimeters times 7.6 centimeters. And let's see what that comes out to. That comes out to 0.4 centimeters, or 4 millimeters if that's what makes you happy. What we can tell about this image also is, since the image distance is positive, it's a real image, which means it's inverted, and we also see that this is a height that is smaller than the object, so this is a reduced image. Everything you already learned to do for mirrors applies to lenses mathematically. You just have to keep the naming conventions straight, like we talked at the beginning of the video, and everything else just kind of falls into place.